The dynamics of leading power factor in AC systems. Defining the leading edge. A leading power factor, PF, occurs in an AC electrical system when the current waveform reaches its peak before the voltage waveform. This condition is fundamentally characteristic of a circuit where capacitive reactance, X_C, dominates the total impedance. It is the inverse scenario of the more common lagging PF, where inductive loads cause the current to follow the voltage. The capacitive cause. The primary cause of a leading PF is the presence of a net capacitive load. While most industrial systems are predominantly inductive, motors, transformers, a leading PF is common in systems featuring large capacitor banks, for power factor correction, long underground cables, which exhibit shunt capacitance, or certain types of electronic loads like lightly loaded variable frequency drives, VFDs, or UPS systems. Reactive power generation. In a leading PF scenario, the capacitive load is supplying reactive power, Q, to the system, rather than consuming it. Conventionally, lagging PF, inductive, consumes positive, kVAR, while leading PF, capacitive, is often denoted as generating or supplying negative, kVAR. This reactive power generation is key to its utility in power systems. The phasing visualization. On a phasor diagram, the current phasor leads the voltage phasor by a phase angle, phi, which is negative in standard engineering notation, or positive when current is the reference. This means the phase angle for a leading PF falls between 0 and 90, or 0 to 90 when the sign is used to denote leading lagging. Voltage magnification, Ferranti effect. A significant effect of a leading PF, especially in long, lightly loaded transmission lines, is the Ferranti effect. The generated reactive power interacts with the line inductance, resulting in a voltage increase such that the receiving end voltage can actually be higher than the sending end voltage. This voltage magnification must be carefully managed. Generator stability issues. For synchronous generators, operating into a highly leading PF can cause major issues. The magnetizing effect of the leading current dramatically reduces the required field excitation current. If the excitation is reduced too far, the automatic voltage regulator, AVR, can lose control, leading to high, unstable voltages, or the machine can slip poles, causing severe damage. The role in power factor correction. The most practical application of a leading PF source, like a capacitor bank, is to counteract the inherent lagging PF caused by inductive loads. By adding capacitance in parallel, the kVAR generated by the capacitors neutralize the kVAR consumed by the inductors, pushing the overall system PF closer to unity. Overcorrection risks. While correction is beneficial, overcorrection, where the capacitive component exceeds the inductive, can itself lead to a system-wide leading PF. This is undesirable as it can result in increased system voltage and the aforementioned generator instability, potentially triggering protective relay trips. Apparent power flow. Like a lagging PF, a leading PF means that the apparent power, S, is greater than the real power, P, because cos, 1. This necessitates larger conductor sizes and higher q-rated equipment to handle the total current, even though the useful power, kW, remains the same. Correction strategy, inductive loads. If a system is operating with a dangerously low leading PF, the correction strategy is to add an inductive load, such as a shunt reactor, to absorb the excess capacitive, kVAR. This is the reverse of standard lagging PF correction and ensures system voltage and stability remain within acceptable limits.